to EC TechNest. This is day 22 of the 100 Days Verilog and Digital Design series. In day 22, we are going to talk about FSM coding styles, the simple one that is one block versus three block. Let us understand first what is one block. As the name itself is suggesting you that we are going to use only one block, and it is going to be a single always block or a process in VHDL. How does it work? You use a single clocked block, that is always block. Transition outputs are updated on the active clock edge. What they mean to say is, if you are working on an FSM module, the states, the transition, and the outputs are all updated in this single clocked block. Here, the thing is, it is very concise, like it is fixed to that only always block. And you see that since everything is inside a clocked block, outputs are registered by default. It is difficult to debug, and where the next state logic ends and the output logic begins. Since you are going to be using a lot of begin, end, and also if and always, that is a bit difficult to debug. Whereas when compared to the three block FSM style, you will have three different blocks: one for the state, one for the transition, and one for the output. One thing to note that it also takes one extra clock cycle. One block FSM takes one extra clock cycle. Here it is given, see. Because output are registered, they will always be delayed by one clock cycle relative to the state transition. That means after the state transition has occurred, for the output to get updated, it will take one more clock cycle, which might not be what you want for a Murray or Mealy machine. So once you have understood one block, it is a bit opposite to three block is a bit opposite to one block. Here the state register, here you will use sequential, a simple clock block that updates the current state with the next state. Here the states keep changing. Next you have next state logic that uses a combinational block, like using always at star. It contains a case statement, and based on it what the next state or the current state should be, it will define that. And last, the output logic. Here it can be combinational or sequential, a separate block that defines the output. Output here depends only on the current state for Murray machine, and Mealy machine it will depend on current state as well as the inputs. Comparison, as we all already saw it here, the style of writing the code is a bit cluttered. Here it is excellent because you are using three separate blocks for it. So it is easy. If you have made any mistake in the state, you can easily debug it rather than searching where have I made the mistake. Maintenance, here it is difficult to maintain. As I told you, it is easy to modify and transitions output. It can be easily modified. If you see a error, it will be easy to debug in three block style. One block style is purely sequential. Here it is a mix of combinational and sequential. Tool optimization. It is harder for some synthesizer. Here it is highly optimized by most tools. Here it has low risks of glitch since the outputs are registered. Here it is moderate if outputs are combinational. So it is preferred to use sequential in the last block here rather than combinational. Let's design a simple sequence detector that looks for the pattern 2-B11. In digital communication, when you are transferring one bits from the other bits, we use something called as a flag. So in this type of things, it sequence detector will become very much important. Now that you have a signal which is of 2-B11, you have to detect whether this sequence is repeating. That means whether you are able to see 1 1 again and again. First, let us see how it is done in one block style. Here we are using a always block triggered by a clock pulse. This is state transition diagram for the sequence detector. Here you have three states, that is S idle and the S1, S2. At S idle, the pulse is nothing but it shows the increment. If data in is here 1, you will move to S1. That means in this sequence, first data is confirmed that it is 1. So now that it is confirmed, you will increment the pulse to 1. Again, you will check here. If the data is equal to 1, you will move to the next state, that is S2. If the data in is 0, that means you got 1 0, you will again move back to idle. Again you will start searching for the next state, and in the S2 you will put the pulse back to 0 from 1, and once you have crossed S2, it is a success state. Let us see it using a Verilog code. You have the module FSM for one block type of writing. Your inputs are clock, reset, and data in. Output reg is pulse. Here you have registered the state as a 2-bit value. Parameter, your what do I say for this? Yeah, you're just assigning some binary value for your states. Always at positive edge of the clock or positive edge resist begin. If reset is set, you will go back to the idle state and your pulse is 0. Else, you will begin your case. Here first you are at S idle. That means your state is idle. Here your pulse is 0. If data in, state will be S1. Now you will come to S1. If data in is equal to 1, you will begin, state will go to S2 and pulse will be incremented. That means it will become 1 again. From 0 it has turned 1. Else it will again go back to S idle. Now you are in S2. You will begin. Now that the pulse has become 0, if data in is equal to 1, state will again go back to S1. Else state is equal to S idle. End case, and you will end the module 2. Now that you have seen the one block style of writing, now we have the FSM for 3 block. The parameters will still remain the same, nothing changes, just the way of writing these 3 blocks will change. Here first I will tell, if reset, your current state will be, that's idle, else you will go back to the next state. It means you will go to the next state, not go back. Always at star begin, case current state. If S is idle, you will go to next state. That is like you are putting a conditional statement. If data in is equal to 1, you will go to S1, or else if it is 0, you will go to S idle. Again, for S1, you are again putting a conditional statement. You are telling that if data in is equal to 1, you will go to S2. If it is 0, again idle. Same way for the last state, S2, we are going to check for the next state. If data in is equal to 1, it is S1, and it will go to, if it is 1, it will go to S1, or it will go to S idle. Default state is your S idle state. Now you will tell that assign pulse is equal to current state and the output at S2. If you have got 1 1, your pulse will become 1. That means you have detected the sequence 1 1. Let us see what was the difference here. Output logic pulse is equal to 1, inside always at positive. Here we are telling in a combinational block, you are using this statement, what we saw here. Here the output is delayed by 1 clock cycle as it has to register it. Here it will do it in immediate clock cycle. Pulse aligns with the end of the state. Here pulse will align at the start of the state. It uses an extra flip-flop for the output because it has to register, right? You use reg. It uses only gates unless you chose to register it. If you have any doubts, feel free to put it down in the comment section. Thank you.